the steady state probabilities corresponding to RE, RB, RC, and RB. So you get 4 vectors. For each of them, you get 1 vector. It's by using this. Solve this jointly. Of course, it's time consuming because you need to compute all the values. So after you've done that, you get all the decisions or variables. So maybe I can write down so here is the policy R0, RA, RB, RC, RD, and here is the steady state probability. And here is the expected value of C. It's not really, here I'm just using EC to represent that, but it's the limit. As you remember, limit n goes to infinity, sum of k from 1 to n, but n goes to infinity, expected value of that. So if I compute those, okay, the first one you remember is something like 7 13s, 2, and the second one is 2 21, 5 over 7, 2 over 21, 2 over 21, and 2 over 7, 11, 1 over 11, 1 over 11. The exact number you can compute. So what about the cost associated with this? Here you have a 1923. Here you have 6. So if I'm looking at this table, by looking at the table, you tell me what is the optimal policy. Yeah, it's the minimum cost, right? So that tells you this policy turns out to be the optimal policy. So what is the optimal policy? You replace at state 3, you overhaul at state 2, bring that to state 1, right? So that's the optimal policy. Now this one is not optimal. You are in state 1, 2, 3. In any one of those, you are going to replace them. Likewise, this one is not optimal either. The first one is not optimal either. The first one is do nothing, only replace when it is bad. But you see, some maintenance is needed to bring the cost down. Okay, so you can see that. This one tells you to get the optimal cost. So I'm going to say a few words about this. With this, you can already solve, I think mostly you can solve the problem. I'll give it to you, but let me say a few words about this market decision pattern, because we are in this chapter, so I better say something about it. So there is something called stationary deterministic policy. So let me say a few words about stationary or stationary policy. And something called deterministic. So what is a stationary policy? Stationary means it doesn't depend on time. So at any time you are using the same policy, it's invariant with respect to time. So that's not depending on time. What about the deterministic policy? Once you decided it's in this state, if you are choosing this action, you will have only very, very specific deterministic outcome comes out. So it's not like with certain probability I'm choosing this, with certain probability I'm choosing that. This one is truly non-random. Okay, so you can think about that as non-random. Think about this one as something independent of time. Okay, so the policy you are going to look at later will be, I think in the problem I gave to you, I think it's deterministic stationary policy. Stationary meaning independent of time. How did we achieve the stationarity? Could anybody help? So as you can see, what we've done here is instead of this instantaneous measure or probability, we are actually using the steady state probability. The steady state probability is independent of time. Okay? Because that's long run at t goes to infinity, that's what happened. So this guy is independent of time. Therefore, this achieved the stationary policy. What about deterministic? Well, here, let me say, so maybe I'll mention a few words about this. So, you know, the policy, a policy, say R, is characterized by the following: P0 R, P1 R, P M R. Again, the subscript denote the state of the Markov chain. In the example we did, we have a D0, D1, D2, D3, no more. But it will be R dependent. For each different R, we have different things. So here, one way to do that is, sometimes people do this, is that you are thinking about it here, you have a state. All right? So let's label the state as 0, 1, 2, up to M. That's the state of the Markov chain. Now here you have the decision. Now for the decision, how many decisions we have? We have from 1 to capital K decisions, right? So I can write this one as D01, D02, up to D0K. And here is D11, D, D11, D12, and so on and so forth. So I have this matrix. The last one, of course, will be DM1, so DMK. Now you see, this is the capital K, by the way. Let's make this pretty large. One thing is that this matrix is not necessarily a square matrix, right? Because in one set, you have the total number of rows. How many of them you have? You have m plus 1 rows. How many columns you have? You have k columns. So in general, it's not a square matrix. But what happens is that because it's the, how do you characterize as deterministic policy? You determine the following way. It's DIK is 0 or 1 option. So DIK equal to 1 if, say, the decision K is chosen for state I equal to 0 else. So this is the purely deterministic quantity. if you look at that, that tells you, in this, if you are talking about the here, in this, in each row, you only have one, all the others are 0. Okay, so that's just the representation. So why we want to write that? Well, there's something called, you remember the first thing we did in this class is linear programming, right? So in fact, we get to this point that I want to conclude that by saying the Markov decision process can be solved by linear programming approach. But this one doesn't seem to be. Why is that? Because linear programming, you remember the basic definition. You don't have to memorize that, but in the problem, you will see some conceptual problem ask you, what are the basic requirement or main assumptions? Linear programming problem asks for, for each decision variable can take any values in any fractions or anything, any real number. But what are the quantities here? What's happening here is that they can only take the value of 1 or 0. So if we want to use linear programming to solve that, that becomes a problem. You see, what's the problem? Because it would not satisfy the basic requirement of the linear programming. It has only 0 it has only the value of either 0 or 1. All right. Couldn't do the tongue twister. So anyway, so then what do? Then people came, decided to use something called a randomized policy. So what is a randomized policy? You can make this in short, say the PIK is no longer 0, 1. It could be 0, or it could be 1. But in general, it's going to be some probability. It's what probability? It's probability decision K is chosen given that is in state I.
Sorry, what does that say? What policy did you say?
Randomized. Randomized, sorry. just as I couldn't do it on this. So, time is running short, that's why. So anyway, there are lots of interesting stuff here to convert this one into a linear programming problem. In fact, as you can see, this is some sort of conditional probability, right? And your stationary distribution or steady state probability, in fact, is true unconditional probability. So what I'm saying is the following. So the typical thing what we do is we define another thing called YIK. Because of the time is short, I will not do the derivation, but I want to write it. It's the probability of state is I, and the decision is equal to K. So it's like an and, right? Is this and that. But this and that, you can write that as, by using the conditional probability, you can write this as pi I times d ik. There's reason why this is equal to that, but if you read the book, you'll see it. So from here, there's a lot of it's not a lot, but some derivation you can come up with the following so-called linear programming formulation. So the problem becomes the following. you compute the expected or long-run average cost, that becomes this. From 0 to n. This is the state of the Markov chain. And your decisions from 1 to k of pi I times CIK. What is CIK? That's in state I, taking the decision k, the cost associated with that, multiplied by DIK. There's a reason how we can get this. It's actually quite nice derivation with this part, except I don't have the time for doing that. And you can see either, you can even simplify this further by writing down this as I from 0 to n, k from 1 to capital K, C I K, Y sub I K. And this is by using that. And then you want to minimize. So you want to minimize C equal to this. And subject to the following constraint, one of the constraints is y from 0 to capital M, k from 1 to capital K of y I k equal to 1. So those are joint probabilities, right? So because of the joint probability, if you're adding up all the i's, all the k's, they should give you 1. So that's one of the constraints. All the other constraints are from 1 to capital K, y sub j k, minus some I from 0 to capital M, k from 1 to capital M, y and a, condition probability Pij k equal to 0. And finally, y I k greater than or equal to 0. I runs from 0 to m. K runs from 1 to capital K. Okay, so that's the linear programming formulation for that. Anyway, so we start with linear programming, we end up with linear programming problem as well. So let me stop here, and let me say a few words about the part 1 of exam test 4 on Thursday. I said 40 minutes for 40 parts. So what should be there? Well, mainly is inventory problems, as I mentioned. I said everyone works out from this room. You should know what the SS policy is. Just pay attention to that, and also, the other quantity. One stage is the stochastic model, and also the deterministic model. Nothing beyond that really is. But the main reason I'm putting there is that last time some of the problems you didn't handle that well. So that's the reason for that. I think, as I mentioned. All right. So. Any questions before I return to the test?
You said that the Markov decision process is going to be on the take-home part of the final?
Yeah.
Like, will it be a very complex problem? Or
I don't think it's very complex, but I think maybe time-consuming. You have to, as you can see, you have to find all the steady-state probability. Yeah. You have to do a lot of computation.
We do? Wait, this Thursday?
For the take-home part, make sure you do it independently. Okay, so that's my request. I trust everyone do that. All right. Okay.
The day after tomorrow?
Yeah, the day after tomorrow.
Oh, okay.
Really,